Thanks everyone for coming. Thanks for inviting me. See that it's really a nice place. I very much enjoyed my stay here. So let's jump into this idea of positivity. So a multivariate polynomial with real coefficients is called positive if it is a non-negative number when evaluated on all reals. So when I say positive, I really mean non-negative. So for example, x squared plus y squared minus 2xy is always a positive polynomial. And by arithmetic geometric inequality, you know when n is an even integer, then the sum of xin minus n times the product of xi's is positive. And also the square of any polynomial is always a positive polynomial. And one of the main reasons we care about positivity is that the optimization problems are essentially positivity problems. So many optimization problems can be formulated as finding the minimal value of maximum value of some polynomial. For example, now we want to evaluate the minimum of this some polynomial f. So if lambda, a real number, is a lower bound of the minimum, it means that f is always greater than lambda, meaning that f minus lambda is a positive polynomial. So the minimal value of f is essentially the maximum value of lambda such that f minus lambda is positive. So if you have an algorithm to solve positivity problem, then you have an algorithm to solve some optimization problems. Of course, this is just a toy model. So in real world, we need to consider polynomials with respect to some constraints. So now our task is to find the minimum of some polynomial subject to some constraints. Well, those constraints are also given by polynomials. So again, it is essentially minimize this polynomial in this quotient ring. So this is the ring of the real polynomials quotient, the idea generated by all those constraints. So the minimal value of f with respect to those constraints is essentially the maximum value of lambda such that f minus lambda is a positive polynomial in this quotient ring. So for example, now we want to find the minimal value of this function to x squared minus yz on the unit sphere in this three-dimensional Euclidean space. So this minimize this function subject to this constraint. So if you do
plus y squared plus z squared equals 1.
Sorry?
The green text.
Oh yeah, there's a typo there.
Signs.
There should be pluses.
Oh, plus. Sorry.
Yeah. But the optimization problem is fine, so you're good.
Yeah. Okay. Yeah, this should be plus and plus. And yeah, okay. So here is also this one is
correct. Yeah, you're good.
So if you do some calculation, you would know that this target function plus 1 minus the constraint can be written as the sum of squares of two polynomials, which is always positive. So in the language of this quotient ring, it means that the target function plus 1 is positive in this quotient ring, meaning that minus 1 is a lower bound. Okay, and you may wonder whether this lower bound can be achieved. Yes, so this lower bound can be achieved if and only if this inequality is saturated, and so you need x to be 0 and y, z are the same. So on the unit sphere, you can take y and z to be 1/√2 or minus 1/√2. Okay. So now optimization problems are essentially positivity problems. So to find algorithm for optimization problems, you need an algorithm to determine positivity. Right. Okay, so now our task is to find an algorithm, take polynomial as an input, accepts if this polynomial is positive, rejects otherwise. And I have a naive approach. So first observation is, if you view polynomial as a function on the Euclidean space, it is a continuous function. And the set of rational numbers is a dense subset of real numbers. So although the definition requires positive polynomial is non-negative in all reals, you can just verify rationals, right? Okay. So in my naive approach, the first step is to pick an order of rational numbers. And then you compute fx1. If it is negative, then it is not a positive polynomial. If it is positive, then you compute fx2 and go on and go on. So if this problem is of course problematic, if I give you a polynomial which is not positive, and you eat a lot of vegetables, fruits every day, and you live long enough, maybe someday you will see some xi such that fxi is negative. Okay, so yeah, so for the no instance, the algorithm at least stop at some point. But if I give you a positive one, then the algorithm will run forever. Right? So the punchline is so the running time of this algorithm is co-RE. So the running time is somewhat non-standard, but the iteration is, so algorithm is RE if for yes instance, your algorithm will accept infinite steps. But for no instance, there's no such guarantee. And co-RE is the complement of RE. So for our algorithm A+, for the yes instance, the algorithm may not halt. But for no instance, the algorithm can reject infinite steps. So the punchline is, the definition of positivity is not a certificate of positivity. Here, when I say certificate, I mean some equivalent condition, and it's also operational, meaning that you can actually run on some computer, tells you the correct answer in finite steps. Okay. So now, seems like positivity.
Is this just an upper bound on the running time of A, or can you actually show that this problem is complete for co-RE?
It's not complete for co-RE. Yeah.
So it's not really true that the running time of A+ is co-RE.
Yeah, so that's not true. Yeah. So yeah. So it seems like positivity is really hard. So now let's think about how do we actually prove some polynomial is positive. Like how do you prove x squared plus y squared minus 2xy is positive? You do not plug in all rational numbers or real numbers. You just do this decomposition, write it as x minus y squared. And in our optimization problem, this target function plus 1 can be written as a sum of squares. So you know minus 1 is upper bound. Okay. So you see some pattern here. So we define the polynomial is a sum of squares or an SOS if it can be written as a sum of squares of some other polynomials. And we use a sigma to denote the set of polynomials that has such a sum of squares decompositions. And we use P to denote the set of positive polynomials. Apparently, if a polynomial can be written as a sum of squares, then it is a positive polynomial. Do we have the other direction? So this question is quite important because the sum of squares is computable in some sense. So if your polynomial indeed has a sum of squares decomposition, then there is some algorithm based on semi-definite programming that can actually output the decomposition. So now, suppose we live in a universe where every positive polynomial has a sum of squares. Then I can combine this sum of squares algorithm, and my naive algorithm gives you an algorithm which tells you the correct answer in finite steps. We just combine these two subroutines in parallel. So if I give you a polynomial which is positive, then the first subroutine will output a decomposition because we assume the assumption is every positive polynomial has such decomposition. So in this case, you know the polynomial is positive. If I give you a polynomial that is not positive, then in my naive algorithm, you will eventually find some xi such that fxi is negative. Then you know this is not a positive polynomial. So now the question is, do we live in such universe where every positive polynomial has a sum of squares? The answer is no. Hilbert proved this in 1888. So not every positive polynomial has a sum of squares decomposition, unless your polynomial is small in the sense that the degree of the polynomial is low and you don't have much variables. The Hilbert's proof, so the punchline is sum of squares is not a certificate. So Hilbert's proof was non-constructive, so it was proved by contradiction. And the first example was given by Moskine almost 80 years later. So this is a polynomial, which is positive. It is easy to prove. And once you can prove that, it cannot be written as the sum of squares of other polynomials. So, wow, so it's hopeless, right? Positivity is really difficult. Although this polynomial cannot be written as a sum of squares, Moskvin shows that it can be written as a sum of squares over some other squares. So this approach gave us some hope. Maybe we can look at some weaker condition. So if a polynomial f is a sum of rational squares, if it can be written as the sum of squares of rational functions, a rational function is just a polynomial over another polynomial. Okay. So if you are a sum of squares, you are of course a rational sum of squares. You just take all g's to be 1. Okay. And the famous Hilbert 17th problem asks whether every positive polynomial can be written as the sum of rational squares, and Artin proved yes. Okay. And good news is there are some algorithms based on semi-definite programming which can also output the decomposition of rational sum of squares. So now positivity is not that hard. You just combine the algorithm for rational sum of rational squares and my naive algorithm. Then if your polynomial is positive, then your first subroutine will tell you the decomposition, then you know it is positive. If it is not positive, then my naive algorithm will find some counterexample in finite steps.
So is there a better way to find this counterexample?
Yeah, you have. Yeah, so this is one of the central questions in the real algebraic geometry. So how to determine positivity or find sum of squares decompositions in a more efficient way. So I only talk about some elementary stuff. So now you can generalize this positivity and sum of squares ideas to many other settings. For example, you can consider some complicated fields other than real number fields, or you can consider positivity and sum of squares on this compact algebraic sets, which is crucial in practical use. And so the study of all those things have some fancy names called positive stances and non-stances. And none of them will be talked in my yeah. So I really want to talk about this positivity versus sum of squares problem in quantum information setting. So in quantum mechanics, if you want to quantize something, you just put a hat on your position or momentum. So the difference is without hat, your variable can only be substituted as a number. But with the hat, now you can plug in matrices or even operators in your variables. So in this talk, I want to consider polynomials evaluated on matrices or even operators acting on infinite dimensional Hilbert spaces. Okay, so for example, if you have a polynomial a0 plus a1t plus an t to the n, plug in some matrix x, here's matrix px, which is a0 identity matrix on identity matrix plus a1x plus a_nx. And the multiplication of matrices is well defined, so there's no problems here. But so this is only a single variable case. For multivariable case, this is problematic because unlike numbers, matrices do not commute. They are working from home. So x1, x2, and x2, x1 are the same polynomial in the classical setting, but they are different if you want to plug in matrices in those polynomials. Okay, and also in quantum mechanics, the matrices we are talking about have complex entries. So for a complex matrix, x squared may not be a positive semi-definite matrix. So we need this star operation here. So x star x is positive. Here star is the conjugate transpose of the matrices. So this leads us to study non-commutative polynomials in star algebras. So the analog of polynomial ring in this setting is the algebra of free algebra, the set of non-commutative polynomials. So this is basically the star algebra generated by 2k variables. So x1 to the xk and x1 star to the xk star, with the constraint that if you take star 2 times, you go back. So if you think of xi as a matrix, it's just you conjugate transpose twice, you get your matrix back again. So here a star algebra is just an algebra equipped with an involution. So this involution, so if you take this involution twice, you get back. This involution preserves the addition and it reverses the order of multiplication. So we can think of this star as just a conjugate transpose for matrices. Okay. So some example. So this x star x plus y star y minus x star y minus y star x is a non-commutative polynomial with 2 variables. Right. So if you plug in some x to little x and y to little y, then it becomes a matrix in this form. And you can actually write it as xy star times xy. And so the Hermitian square of any matrix or operators is always positive. So this is indeed, so you can think of this as a positive non-commutative polynomials. So here, when I say an operator or a matrix is positive, meaning that it has no negative eigenvalues, no negative spectrum. Okay. So now we also need to consider non-commutative polynomials with some constraints. So for example, now you want to find the maximum eigenvalue of this polynomial, x star y plus y star x, when plugging unitaries. So you have a constraint that your variables are unitaries. So in this case, for any unitaries x and y, 2 times identity minus fxy can be written as this thing, because you can just replace the first identity as x star x, second identity as y star y, and this goes back to the previous expression. So you can still express it as a Hermitian square, which is a positive semi-definite matrix. Okay. So in the language of star algebra, this means that 2 minus this non-commutative polynomial f is positive in this quotient algebra. So this is the free algebra quotient, the two-sided idea generated by your constraints. So now our constraints is x star x, x star, y star y, y star are all identity. So we have some notions of this star algebra. So we use this CFA to denote the free group algebras. Basically, the group algebra of the free group generated by k variables. So so if you want to plug in matrices in this algebra, you must plug in unitaries. This is the requirements of this algebra. In quantum information, we also have this observable algebra models, the measurement operators, the binary with binary outcomes. So this is the algebra generated by k free product. So this star is not a star involution; it's the free product. So k free product of Z2, and Z2 is just a Z mod 2Z. So generators in this group has order 2. And they are unitaries. So they are binary observables with 2 outcomes, like X or poly Z. So, so if you want to plug in matrices or operators in this algebra, you must plug in observables. Okay. So there are some more rigid way to talk about plug-in matrices, plug-in operators. So you can use the language from representation. So indeed, if you plug in an xi to some variable xi, it means you have a star representation which sending your little xi to this operator xi. So here a star operation is just a map that respects all the structures of the star algebras. So it is linear, it preserves multiplication, and it preserves star condition and star involution. And we say this representation is finite dimensional if the space H is finite dimensional. Here, B of H is the set of bounded operators acting on H. When H is finite dimensional, you can think of this as a set of matrices. Okay. So so the punchline is you plug in some matrices xi to your variable xi, meaning that you have you define some representation that's sending finite dimensional representation, sending your little xi to capital xi. So this is just a more mathematical way to talk about this plugging things in your operators, in your polynomials. So now we have this notion of noncommutative polynomials. So we want to study the problem of positivity versus sum of squares in this setting, which is closely related to quantum information. So here, if I give you a self-adjoint element, I can define this element is a sum of squares if you can find some other elements such that F is a sum of Hermitian squares of those elements. So this is really a sum of Hermitian squares. And we say an element in a star algebra is positive if you apply any representations. It is the resulting operator is always positive. Or in other words, a polynomial or element is positive if it is positive when you plug in any operators, possibly infinite dimension. And we call a polynomial or an element is matrix positive if it is positive when you plug in matrices. So it is positive on the finite dimensional representations pi of this algebra. Are there any questions about this definition? Good. So sum of squares is just it can be written as a sum of Hermitian squares. Positivity meaning that you are positive when plugging operators. You are always positive when plugging operators. Matrix positive meaning that you are always positive when plugging matrices, plugging finite dimensional operators. Okay.
So sorry, one thing. With NC polynomial, did you imply now unitary, or was that just as a side track? Are the operators always unitary here?
No.
It
depends.
Okay.
What is your algebra A?
Yeah.
So your algebra is free algebra, then there's no
Just a free
restriction.
Yeah.
So if your algebra A is the free group algebra, then the guarantee is the promise is you need to substitute. You need to plug in unitaries. For the algebra of observables, you need to plug in observables because the star representation needs to respect the structure of the spin.
In 2 and 3, so this bigger than 0 is positive eigenvalue.
Yeah. So
Yeah, it's like the same as in your.
yeah.
Yeah, it's like state in, state out. This is the more general definition.
So So this means it has no for matrix. It has no negative eigenvalues. For operators, it means spectrums are always non-negative. So clearly,
The algebras are considered don't have any topology or norm. Right?
no. Yeah, it is an algebra. So so an algebra is just a linear space which you can multiply vectors, and it's also equipped with the star representation. So there's no topology.
Is there any notion of rational functions in this setting as well?
You will see there's no need.
Okay.
So clearly, sum of squares implies positivity, implies matrix positivity. Because if a polynomial can be written as a sum of Hermitian squares, then plugging any operators, it is always positive operators. And if you are positive, meaning that you are positive in all representations, and finite dimensional representation is just a subset of, it's not a set, it's a subclass of the class of all representations. So if you are positive when plugging operators, of course you are positive when plugging matrices. So the question is, what is the relation between do we have 2 from 1 or do we have 3 from 2? Like whether every positive polynomial can be written as the sum of Hermitian squares, and whether polynomial is positive if you only need to verify finite dimensional. And this is the surprising result. For all those prototypical examples, we know for free algebras, for free group algebras, for the algebras that models quantum measurements, 1, 2, 3 are equivalent. So every positive polynomial is indeed matrix positive and has sum of squares. So sum of squares and the matrix positivity, they are certificates of positivity in free algebras and in all those algebras. So so this result has has many nice consequences in quantum information. I wanted to show you some examples. For example, so now given a local Hamiltonian, you want to find the ground energy. So if your Hamiltonian says is 2 local or 5 local and is coming from some circuit to Hamiltonian construction, then you would have some promise that this ground energy is either lower than alpha, or higher than beta, with beta minus alpha has a inverse polynomial gap or a constant gap. It depends on your settings. So this is a QMA complete problem. So it's kind of a hard problem. However, if for some lambda, if you can write your H minus lambda identity as a sum of squares, then you know your lambda must be a lower bound of your ground energy, because the right-hand side is right-hand side. Your right-hand side, Your right-hand side is a sum of Hermitian squares. It's positive. So H is greater than lambda I, meaning that lambda I is greater than lambda. So lambda is a lower bound. So this tells us in classical setting, if you want to have a better classical algorithm to estimate the ground energy, you can first find some better algorithm to decompose the matrix or a polynomial as sum of squares. If you have a nice algorithm which tells you, well, you can only search sum of squares in those degrees up to those terms, you will always find your sum of squares, then you will have some nice algorithm to estimate your ground energy. And I also want to talk about some applications in the spell inequalities. So in this bipartite scenario, Alice and Bob, they are 2 non-interacting parties. Each of them can make some measurements. So A0, A1 for Alice, B0, B1 for Bob. Those are all binary observables, and they use so their measurement observables are compatible, meaning that they are commute, and they want to measure a state psi. And Bell inequality tells us this expectation A0, B0 plus A0, B1 plus A1, B0 minus A1, B1 on the state psi is always upper bounded by 2 when your observable is indeed some classical random variables. So this is bounded by 2. Even Alice and Bob share some randomness. This is proved by Bell. And the violation of Bell inequalities is that if you indeed have higher dimension measurement operators and your state has some entanglement between 2 parties, then you can achieve some expectation better than 2. And the question is, what is the best rate you can achieve? What is the maximum violation of Bell inequalities? So Silverstone proved that even with quantum entanglement, even with quantum measurements, the best you can achieve is 2√2. So this thing is always upper bounded by 2√2. And it's very easy to prove using sum of squares. So you just use 2 root 2, subtract this expectation, do some math. You notice this is the expectation of R1 star R1 plus R2 star R2, where R1 is A0 minus B0 plus B1 over 2, R2 is A0 minus B0 minus B1 over 2. So this thing is always greater or equal than 0. So this part is always less than 2 root 2, no matter what observables you plug in into this expression.
Are you using commutativity here?
Yeah, I'm using commutativity. Yeah. So so in the language of nonlocal games, I assume this is a commuting operator strategy. Okay. And so sum of squares tells you what is upper bound or lower bound. It also reveals more information about how those bounds can be achieved. For example, if sum A0, B0, A1, B1 actually achieve this bound, meaning that this inequality is saturated, meaning that each Hermitian term must be 0 on the state. So psi R1 star R1 psi is 0, meaning that R1 apply on psi is a 0 vector. So 2 root 2 is achieved if and only if you have this system of equations. And after some linear algebras, this system of equation actually has a unique solution. So your A0, B0, A1, B1 must be Pauli measurements acting on different tensor factors, and your psi must be the maximally entangled state with local dimension 2. Okay, so here in mathematics, when we say unique, we often say unique up to something. So this is not really unique. So this is unique up to local.
Is there some sort of approximate version also of this argument to get the rigidity?
Yes. So that's a very nice comments. Yeah. So so the nice thing of this sum of squares decomposition is even if your 2 root 2 can be only achieved with some epsilon, like the expectation is 2 root 2 minus epsilon, you can still conclude that this vector is very small. And you can conclude that all those A0, A1, B0, B1 are close to these operators in some sense. Yeah. So this picture is called self-testing, and the picture you mentioned is called a robust self-testing. So yeah, so sum of squares is a very powerful tool in self-test. So now I want to.
Does it sort of follow automatically? Like if you have a good sum of squares decomposition, then you get a robust self-testing?
Not really.
Okay.
And so now I want to restate this whole picture in the language of star algebras. Okay. So what is the star algebras underlying this picture? It is the star algebras of the cross product of two free products of Z2. So this Z2 is basically generated by little a0. This is generated by little a1. And this one is correspond to Bob's operator B0. This one is correspond to Bob's operator B1. And your constraint is A0, A1, B0, B1 are observables. But now here there's no Hilbert spaces. So this is just abstract observables. They satisfy the identity where A0, B0, X star X equals X star equals X square equals identity in this algebra. And you also have this constraint that the commute. And the product of group, the group algebra of the product of the group is equal to the tensor product of the group algebra of the group.
Look at it.
So the noncommutative polynomial here is just a0 b0 plus a0 b1 plus a1 b0 plus a1 b1. So this is an element in this style. So let's translate the Bell inequality. Bell inequality just says that 2 minus beta is positive in all one-dimensional representations. So beta is less than 2 if your variables are all classical variables. Okay, but it's not positive if you allow higher dimensional representations. So this is the max. This is a violation of Bell equivalence. And series on bound is just 2√2 minus beta can be written as the sum of squares. Okay. And since it is a sum of squares, it is also a matrix positive. So if you plug in any matrices, this is still positive. And if you plug in any operators, this is still positive. So 2√2 is the maximum violation you can achieve, no matter what strategies you are using. So you may notice the story here is a little different from the story I told you before. Previously, we know that sum of squares equivalent to positivity is equivalent to matrix positivity if you only have a single free algebra. So if you have if you just have one lab, there's no entanglement between other labs, then optimization problems are easier because positivity is equal to sum of squares is equal to matrix positivity. So what about tensor product of free algebras? So those algebras are more important in quantum setting. Say if you have two labs, you want to optimize some functions, maybe winning probability of non-local games or other stuff. So now I wanted to talk about positivity and sum of squares in this tensor product of free algebras. So again, let A be one of those prototypical examples we have, and let F be a self-adjoint polynomial in tensor product of this algebra A. So we still have the same notion. F is a sum of squares. It can be written as a sum of permission squares. F is positive if it is positive in all representations, if it is positive when plugging operators, if F is matrix positive, if you plug in matrices is always, the resulting matrix is always positive.
This might be a silly question, but how much should I think of this tensor product as sort of a normal tensor product of matrices? Because those A's can be very general, right?
Yeah.
So it just works the normal way, or is there something special going on there?
Yeah, so I guess your question is like how we actually plug in matrices in tensor products. Right? Yeah, this is a very good question. So your question is essentially a coins embedding problem. Yeah, the Hilbert conjecture, I guess. Series problem.
Makes me sound smarter than I am, but
yeah. So so for the matrix positive case, so so apparently, if you give a polynomial, say maybe x1 tensor product y2, something like that, there are two ways to plug in matrices or operators. First, you can send x1 to some matrix x1, and y2 to some matrix y2, and in this case, this polynomial will be sent to x1 times y2, tensor product y2. But we know in the group algebra level, the tensor product is essentially commuting relations. So you can have another way to plug in matrices. So you send the x1 tensor identity to some x1, and identity tensor y2 to some y2 tilde, and you have a constraint that x1 tilde y2 tilde commute with each other. So so for the matrix positive, those two notions are the same. You can think of this if you are working in nonlocal game. You can think of this as finite dimensional commuting operator strategies are essentially tensor product strategies. There's no difference. And so if you want to prove this as a homework today, you can think of the structure theory of C-star algebras. So any finite dimensional C-star algebras can be decomposed as direct sums, and Alice operator only acting on some factors, Bob's operator acting on some other factors. So you have this double commutant decomposition. You can use these tools to prove. And for the positivity. Yeah, okay. So yeah, and so although here when we define the matrix positive, we allow plugging any matrices. Right? So there's no dimensional restriction on the matrices you pick. So although those matrices are finite dimensional, but you can have a sequence of matrices which has larger and larger dimensions. Right? So so essentially what I want to say is there's no need to distinguish these two cases when you finite dimension, they are the same. This is also not necessary to distinguish them in infinite dimensional case, because if one thing, if a polynomial is matrix positive in this scenario, it is also matrix positive in this model. If it is positive in this model, it is also positive in this model. Okay, so we also have this sum of, oh, by the way, so thanks for the question, and I want to clarify that here when we say plug-in things, we use this one, the commutative, the canonical, because on the algebraic level, there's no tensor product structure in the algebraic level, they are just the commuting pairs. So we still have this sum of squares implies positivity, implies a matrix positivity. And now question is, okay, do we have every positive polynomials in tensor product as a sum of squares? And do we have every matrix positive polynomials is positive? Okay. And the second question is essentially coins embedding problem. Coins embedding problem, the original version is whether every hyperfinite to one factor can be approximated by finite dimensional von Neumann algebras, matrix algebras, and it has some variance. So here you can think of this as the series sum problem. So now you have a nonlocal game. You'll know the maximum winning probability using finite dimensional strategies 1/2. Right? So this is basically 1/2 minus something is matrix positive. Now you would ask, okay, if I'm allowed to use infinite dimensional resources, can we do better? So the recent and remarkable breakthrough MIP RE tells us, yes, you can do better. So matrix positive does not imply. So there are some functions in the tensor product of free algebras that is positive if you plug in matrices, but you can find some operators when you plug in those operators, the resulting operators can have negative spectrum. And with Arthur Mehta and William Slofstra, we show that not every positive polynomials has a sum of squares decompositions. So in tensor product of free algebras, all three concepts are distinct. Okay. And how do we prove this? We essentially prove that determining positivity is much harder than solving sum of squares. So on the last part of my talk, I want to convince you that positivity in product algebras.
So it's not constructive. It's not constructive. Yeah.
What is the sense of
your result determining positivity? It's not like you're going to give us an example.
I'm not.
Moskin did that.
Well, it's possible to find an example in the future.
That's a very non-constructive statement.
So positivity is indeed undecidable in the product algebras, in the tensor product of free algebras. And how do you prove something is undecidable? You do the reduction from the halting problem of training machines. So here, for any, so if you fix a universal Turing machine, then for any universal Turing machine, whether on the input M, whether it is hot or not, is a RE complete problem. products, undecidable products. So fix a universal Turing machine, we construct a computable map from the input of the Turing machine to some polynomials in this tensor product. So this M is the input of N, is the input of the Turing machine, and this PM is a noncommutative polynomial in this tensor product of algebras that models quantum matrices. So this map has the property that this polynomial is positive if and only if this Turing machine does not halt on the input. So using this theorem, we can claim that determining positivity in tensor product of these free algebras is co-RE hard. So why? So suppose you have an algorithm, you have an oracle to positivity. Then given a Turing machine M, you may wonder whether this M is hot or not. Then you can just run your oracle of positivity. So if you find out that your PM is indeed positive, then this Turing machine does not halt. So it solves a co-halting problem.
What is this N there? Is it a typo?
And the number.
At the end of the theorem.
Yeah.
Oh, I see. Yeah, should be M. Okay, thank you. Yeah. So does not halt on the input M, right? This is the input M.
What's the K in this here?
Oh, K is yeah. So K is some integer that is large enough, and in 2 slides later I will show you what is this K.
It's a constant.
It is a constant. It is roughly around 200.
Okay.
So it doesn't depend on the Turing machine.
Oh, okay. Yeah, it's a constant. Yeah, it's roughly around 200. Yeah. So yeah, 200 is enough. Yeah, you can now think of K as 200.
Okay.
So determining positivity is quite hard because if you have an oracle of positivity, then you can solve the co-halting problem.
Which is a Turing machine does not halt on any input.
Yeah.
Is that correct?
On this input. So
On
this is
specific
a
input.
yeah, on specific input. Okay. So yeah, so the co-halting problem for this universal Turing machines,
Yeah.
your input is M, your output is yes if it does not halt, no if it is halt. This is the co-halting problem. And on the other hand, so if a polynomial has a sum of squares decomposition, then there are some theorems tells you the number of terms and the degree of all those polynomials are bounded. So you can always search. So so if a polynomial has a sum of squares decomposition, then you can always output this sum of squares. So this is indeed at least in RE. So in recursively enumerable language. And positivity is co-RE hard, sum of squares is in RE. These are 2 different complexity classes. Sum of squares is a subset of positivity, but determining positivity is much harder than determining sum of squares, meaning that sum of squares is properly contained in the set of positive polynomials. So not every positive polynomial has a sum of squares decompositions. And you can also see there's no certificate of positivity in tensor product of free algebras because positivity is undecidable. There's no operational way to determine positivity. And so I want to show you the last step of the proof of this theorem. So what does this PM looks like? So indeed, we can find a computable map, sends any input M to a set of polynomials, which depends on M in this star algebra, and a positive polynomial alpha M in this algebra. Our PM will looks like the sum of Hermitian squares of polynomials in Rm minus this positive terms. So it is essentially a positive terms minus a positive terms. And The cool thing of this construction is on each running step of this Turing machine, you can update an estimation of this polynomial, alpha m, with respect to all those polynomials. Okay, so on the running step n, if your Turing machine hasn't halt at the nth step on the input m, then you have such estimation such that the the minimal eigenvalue, the minimal spectrum of alpha m must be greater than 1 over 2 to the n. And it is also bounded by 1 over 2 to the n plus this sum of squares. Okay. So here, notational is, so a polynomial is less than another polynomial, meaning that this polynomial minus this polynomial is positive. So this is, so on each running step, you can estimate.
Positive means that
It is positive in all representations.
Yes, okay.
It is
So
no
that's
non-negative.
yeah. Sort of distinguishing between different definitions of positivity, so it's important.
So here we only talk about the real positivity. So case one, suppose this m is a non-halting case. So in this estimation, you can take n goes to infinite. So this alpha m will be always bounded by the sum of squares terms. So Pm is the sum of squares terms minus alpha m. It is positive. So based on this estimation, you would know if m does not halt, then this Pm is positive. On the other hand, suppose this Turing machine on the input m halts at the nth step. Then we can construct a representation pi and a state psi such that the expectation of pi r star r on psi are all zeros. But this upper bound can be achieved using this representation and state. So in this case, the expectation of pi alpha m on psi is 1 over 2 to the. Now, based on our construction of Pm, the expectation of Pm on psi is the sum of this thing minus this thing, which is minus 1 over 2 to the n, which is negative. So you found some representation pi which has negative eigenvalues. So in this case, your polynomial is non-positive because it has negative eigenvalues. Okay, so this is the last step of construction. Yeah, and you may wonder, how do we exactly define this map, computable map, from M to this set of polynomials and positive polynomials, such that you can have this nice estimation on each step of Turing machine. So I'm not going to dive into the details on how we construct this. I want to convince you that although halting problem or co-halting problem for Turing machines is a giant monster, it can be still encoded in some small algebras. So now our goal is to encode this computation of this Turing machine into a finitely presented algebra. So this algebra has finitely many generators, finitely many relations. So it can be recognized by computers. The computers can store all the relations and the generators. Okay. So the first step is to encode the computation of this Turing machine in a recursively presented group with infinitely many generators, infinitely many relations. But still, this group is conceptually simple. How do we do this? So on each input m and each running step I, we associate two variables, xmi and zmi. We require them, xmi's and zmj's, the commute, unless your Turing machine halts at the nth step on the input m. In this case, we require them anti-commute. So this group has infinitely many generators. So every xmi, zmi is a generator. It has infinitely many relations. You have all those commutation relation, anti-commutation relation. But this group is encoding the computation of the Turing machine in the sense that now you wonder whether this Turing machine is hot or not on the input m at the step n, you just check whether x and n and z and n is commuting or anti-commuting. If it is commuting, then it hasn't hot. If it is anti-commuting, then the Turing machine hots at this step. So we have a group with infinity generators and infinity relations, and we use some techniques from geometric group theory to embed this group into a finitely presented group, step by step. Okay. So this step uses the construction of HNN extensions. It basically adds more relations, but reduce the number of generators to finitely many. And this part, we show that since this finitely generated group has some nice property, it has a so-called polynomial word problem. So you can identify whether an element is trivial or not very quickly. This group can be embedded into a finitely presented group using so-called HNN extensions. So now we encode the computation of this universal Turing machine in a small algebra, in the sense that it has only finitely many generators, finite many relations.
Is this where the 200 comes from?
Yeah, exactly. So what is K? K is basically the number of generators. And the set of relations is basically this set of polynomials. This R is actually relations from this group. So, so those are the intuitions behind this result. Great. So I'm approaching the end of my presentation, but it's not the end of the story. We show that the positivity is core hard, but what is the exact computational complexity of this problem? Okay, so we conjecture that it is also RE hard. Okay, so what are the consequences of this conjecture? So in fact, we know this coins embedding problem, one of the biggest problems in operator algebras. It has many equivalent formulations, like Stephenson's problem, Hilbert conjecture, or whether something is nuclear or not, or whether something is residually finitely dimensional. Okay. So this is related to the question whether the tensor product of free algebras is residually finitely dimensional, RFD. So a thing is RFD, intuitively you can think of RFD is something like non-positive and non-matrix positive are the same. Okay. So it's not exactly the same thing, but you can think of this non-matrix positive and non-positive. So if you want to know something is not positive, you only need to search finite dimensional representations. Okay. So it has been shown that if coins embedding problem is true, then the tensor product of free algebras is RFD. But now we know it is not true, so it is not RFD. This is not equivalent. However, the proof in MIP RE is quite difficult to understand. So if we can prove positivity is RE hard, this also implies non-matrix positive and non-positive are different. Implies tensor product of free algebras is not RFD. Implies coins embedding problem is not true. So if we can prove positivity is also RE hard, this can be a new proof to coins embedding problem to MIP equals hard.
Which you hope is less than 100 pages long.
I don't know. I mean, over the past 40 years, mathematicians can only prove this is equivalent to this, this is equivalent to this. No one dare to prove the theorem. Right? So I'm not claiming this one is easier to prove. Yeah, it's just my hope. Okay. So that's all. Thank you.